Hello everyone, and welcome to our project presentation, ManipTrans extending to new Dexterous hand DG-5F. In embodied AI, imitation learning has shown great promise, but it heavily relies on high fidelity and large-scale training data. Traditional real-world teleoperation for data collection is expensive and often unstable. A ManipTrans framework was introduced to address this, leveraging massive human motion capture datasets to train a reinforcement learning strategy that translates human skills into executable robot trajectories. There are two difficulties we encountered when trying to deploy ManipTrans on DG-5F. First, ManipTrans doesn't support DG-5F, so we try to extend the framework. Second, DG-5F has substantial morphological differences from human hands. So we redesigned the preprocessing loss from absolute position difference to shape-similarity. Let's briefly introduce the ManipTrans framework, a two-stage reinforcement learning pipeline. So ManipTrans actually have three important components: imitator, residual module, and preprocessing. For the imitator, it learns generalized human hand motion patterns. And for the residual module, it focuses on hand-object interaction within one specific sequence. And for the preprocessing step, it optimizes the robot hand pose to approximate the human motion and generates the reference state initialization starting pose. So actually, this is important for the quality of residual learning. We extend ManipTrans to DG-5F by setting up config and UIDF files, and we test the extended ManipTrans on two demos. In mouse rotation demo, we found out that residual module initially failed to converge. The problem is that DG-5F have a morphological difference from human hand, and the solution is to relax the hand key point failure criterion in residual learning stage. In put-off-alcohol burning demo, the policy still failed to converge after we changed the criterion. And we found out that the problem lies in preprocessing, because preprocessing relies on absolute human key points, which result in distorted DG-5F poses. The original preprocessing objective is to minimize difference between the absolute key point position. In our solution, we decouple the optimization of hand shape from global wrist pose. So we reformulate the primary alignment term to operate in a wrist frame. The below table shows the detailed loss function. We evaluated our modifications across 13 manipulation sequences from the OG2 dataset, as illustrated in Figure 4. Our average success rate of 38% significantly outperforms the original method's 28%. In many specific tasks, we achieved substantial improvements, for example, reaching 98% success in the remove USB task. Figure 5 shows the progress made before a task failure. Our average progress increased from 34.57% to 46.58%. This demonstrates that our changes improve the overall robustness and partial task completion of the policy, especially in tasks requiring delicate hand-object interaction. Here we show the detailed task description for each data index, and also some qualitative results. And here is a video. The original failed to complete the whole task. Our project successfully extended the ManipTrans framework to the DG-5F Dexterous hand, despite the large morphological gap. And we generate stable, physically possible initial poses via wrist frame preprocessing and joint regularization. Future works includes improving policy robustness and generalization, extending to bimanual manipulation, and sim-to-real transfer.